So my goal in this presentation is to try to discuss if there are some, 1 second, please. If we can try to develop some techniques that will allow us to reduce the energy consumption and therefore to improve the energy efficiency by doing coding in 3D technologies. I see that there is a lot of echo.
Yes, for somehow. I think, Tahan, if you can close your mic. Now, maybe it's better.
Perfect. So shortly about me, my name is Alberto Garcia-Ortiz. I'm professor in the University of Bremen. And you see that I have a very strong accent. I'm coming originally from Spain. The work that I want to present today has been done in collaboration with the University of Magdeburg. And we have this collaboration in two directions. One is in the direction of low power coding for more classical technologies, like, for example, the chiplet technology or the TSV technology that we have been seeing in the previous presentations. Part of these results, we can find it in our book about 3D interconnects. Nevertheless, what I would like to focus today is in the goals of coding, but when we try to move in newer technologies, and in particular in monolithic technologies. So in short, the goal of our presentation is to try to answer the question whether we can use low power coding techniques to try to improve the reliability and the energy efficiency of the 3D technologies. So that means if we can reduce the power consumption. We want to target monolithic 3D technologies that, as we will see in the next slide, are especially challenging because they are strongly heterogeneous. So the different tiers that we have are going to come fundamentally from different technologies. And because of that, the kind of drivers and the parasitics that we have for the wires in the different tiers are going to be completely. In order to analyze the energy consumption, we are fundamentally going to try to work in two directions. The first is the energy modeling. So what we are going to do is to try to develop one model that is able to predict the power consumption when we transmit information through the wires in a monolithic approach, with the special point that we want to take into account that when we are sending data in these heterogeneous architectures, the fact that the speed of movement of the transition is not the same in all the lines changes actually the power consumption. It is not only that the power consumption depends on the particular pattern that we have to switch in, it is also that the alignment of the signals plays a major role. Once we have able to model the energy consumption in monolithic 3D technologies, what we would like to propose is some low power coding approaches that can be used to reduce the power consumption. The key challenge in this third point is that since we are addressing monolithic technologies with the amount of wiring of vertical interconnect that we have is huge, the overhead that we can have for the low power coding has to be extremely simple. What we are going to develop is a very small module fundamentally based in a set of XOR gates, which is able to reduce most of the, let's say, redundancy that we have in the data, just with a cost which is fundamentally proportional to the number of lines, so extremely small. So let's start with the motivation, why to try to address coding for these fine pitch 3D technologies. If we analyze the landscape of 3D technologies, we will see that classically we have been working in 3D technologies that have a very sparse, let's say, number of tiers. For example, in the previous presentation, we were learning how to handle temperature effect in in the stacking of different chips, fundamentally at that, the kind of granularity that we have for the vertical interconnect is the one of the TSVs, and because of that, far below this limit of 5 micrometers. If we want to develop 3 technologies that allow us to separate, to disaggregate the part of a system on chip, separating at the level of the gate between the different technologies, then we are going to need a kind of density for the vertical interconnect, a kind of pitch, which is below 5 micrometers. Today, the candidate technologies to try to have this very dense 3D interconnect are on the one side, the electric bonding with VLRs or hybrid bonding. With that, we can get close to 400 nanometers in terms of interconnect. If we want to move even further in terms of interconnect, our next candidate is monolithic 3D. And actually, this is going to be the target for my presentation today. If we try to understand a little bit more generally how monolithic 3D works, you will see that fundamentally we are processing one tier here, what we have in the lower part with aluminum in terms of the lower interconnect, MP between 1, 3, and maybe middle interconnect, maybe another three layers. Once we have implemented this low technology with the layers, then we would like to add another tier, and on top of that, to continue with the metallization. The advantage of this kind of technology is that by doing this, let's say, interconnect in terms of tiers implemented sequentially, we can get a very, very high density in terms of vertical interconnect. Nevertheless, this kind of technology had some fundamental, let's say, limitation. The first one is that when we produce the devices, the transistors that we have in the upper layer, the temperature profile that we are using is affecting negatively the chip that we have produced in the lower part. Because of that, typically we have to use technologies which are limiting dramatically the temperature during the processing of the upper tier. This, in the praxis, means that the kind of transistor that we have in the upper tier fundamentally are slower, are of a lower quality than the transistor that we have in the bottom tier. We can try to model that just assuming that the 2 tiers have technologies which are, let's say, different. The second fundamental limitation is that since we want to connect with a fine pitch the low tier with the upper one, we see that the amount of wires that we can use there is actually much more limited. Even worse, since once we have implemented the metallization in the bottom tier, we want to implement the upper one, the temperature that we have to use should not degrade the metallization down. And because of that, we are really limited in the amount of materials that you can use for the bottom technology. This fundamentally means that the resistance that we are going to have in this bottom tier, that the quality of the interconnect that we are going to have in the bottom tier is actually worse than the interconnect that we have in the upper tiers. So if we try to, let's say, summarize this, the fundamental message is that in monolithic 3D, we have a very highly heterogeneous scenario, where in the bottom tier, we have fast transistors with slow wires and limited wires, while in the upper tier, we have slow transistors, but a lot of interconnect and very fast wires. In this slide, we have just a short idea about how is the implementation of the monolithic 3D. Fundamentally, we are starting with one wafer where we implement the transistors, then the metal interconnect. Once this bottom tier is implemented, we can somehow glue another tier using a technology which is very, very similar to the process that we were using for the wafer to wait for connection with hybrid bonding. After that, we can thin the upper tier, and fundamentally, we will get the layer where we can implement the transistor. In the next step, we will start implementing the transistors of the upper tier. Then with the help of MIVs, we can add some interconnect between the upper tiers and the lower tiers. After that, we can continue the implementation of the metal layers in the upper tiers fundamentally without any restriction. And then on top of that, if we want, we can add TSVs or C4 connections, just connecting this element to the upper one. Again, you see that the key message is that if we are using this technology, we have a very high degree of heterogeneity. So what is our goal? Fundamentally, our goal is to try to understand, to try to model the electrical characteristics that we have in this kind of monolithic implementation connected by MIVs, to have a look to our system and to try to see if we can connect elements that, for example, are in the upper and that then have to be connected to the lower vias using a set of optimized wire structure with the optimal number of buffers. And in addition to that, taking into account that for the connection, let's say from the memory to the lower tier, we can use this small block that we have in green, this decoding logic to interpret the values. If we think in terms of the transmission of data, in principle, you should say what I need is an encoder for the upper part and then a decoding in the lower part. It turns out that in a lot of scenarios, it is possible to encode the information already before saving it into the memory in such a way that actually the only overhead that we have is to do the decoding. So then our challenge is how can we determine the optimal number of repeaters and buffers that we have in our interconnect? How can we determine which is the part of the wiring that should go in tier 1 and in tier 2? And finally, which is the optimal low power coding that we can use to try to decrease the energy to the maximum. In this slide, you get just one example of the kind of heterogeneity that we are analyzing. We want to develop a methodology that allows us to study different technologies and to model different technologies, making sure that even if we have some changes in the technology because of some, let's say, improvement in technology, that nevertheless our methodology will be able to capture that. Because of that, we are analyzing a very broad set of technologies, probably broader than actually what you can find in reality. In terms of the bottom tier, we are assuming that we have technologies that can go from the equivalent to 3 nanometers to the equivalent to 18 nanometers. In terms of resistances, you see that we are ranging the resistance of the wire from 77 ohms per micrometer when we are using a very dense technology, 3 nanometers. And then if you are using, let's say, older, more classical technology, for example, 18 nanometers, then we are assuming that then the resistance will be slightly better, 23 nanometers, 23 ohms per micrometer. In terms of a capacitance, the variation is slightly slower. In terms of coupling capacitance, we are ranging from something like 60 attofarad per micrometer to something like 51 attofarad for micrometer. We were also modeling the ground capacitance, where actually we have some changes. And you see with that, we can already get a broad spectrum of, let's say, typical scenarios. In terms of the top tier, we are assuming that the technologies are older, and fundamentally we are using technologies ranging from 7 nanometers to a very, very old 65 nanometers, probably much older than what you will get in the praxis. And again, we are modeling the resistance and the capacitances. You see that this time the resistance, the values of the capacitance that we get are slightly better. We are assuming that in the top tier, we have a wider set of interconnect and that the interconnect are actually better. We did for parameters. The first thing that we did is just to do 3D simulations. So 3D in the sense of simulations in the 3D domain so that we can characterize the resistance, inductance, capacitance of all the interconnect in all these technologies. Once we have this model for the wire, we were just fundamentally looping all over all the scenarios in terms of the separation between metal lines, the width of the metal lines, and the strength of the wires. And for that, we were calculating the energy consumption that we have in the different configurations. In the slide, you can see as an illustration a configuration where we have only in one tier, but obviously we did the same simulations when we go from one tier to the other tier. If you try to simulate just one interconnect in one single wire, then actually the number of simulations is relatively simple. In our case, since we want to understand low power coding, we were actually simulating the delay and the energy consumption that you get when we are sending any pattern of 4 bits through our extracted interconnect architecture. So we were simulating something like 6,000 scenarios per every case. We wanted to compare this, let's say, empirical data with the mathematical model. And for that, fundamentally, what we can do is just to try to analyze how can we model the energy consumption in an interconnect. This is a classical result where you are in 2D. Fundamentally, if you have two lines, then the switching activity of one of the line versus the other one produce an energy consumption. The energy consumption is fundamentally the integral of the voltage, which is a constant, times the current, which has a very strange shape depending of the nonlinearity of your CMOS technology. Remarkably, when you try to calculate analytically this result, actually you can calculate a closed formula. So this VDD squared CI jot multiplied by the bit in the line K and multiplied by the variation of the BK minus variation of the B cut. And this formula actually agrees extremely well with the simulation result, even if you have more than one aggressor, even if you are in a scenario like TSVs where you have more than one line, which are, let's say, adding one coupling capacitor. You can try to reduce the formula even further. You can see that fundamentally the energy consumption that you get is proportional on the one side of the factor CII, which is related with the ground capacitance that the interconnect in 2D or 3D is seen. And then we see I jot, which is the coupling capacitance that the interconnect is seeing between two networks. From the point of view of the data that we are sending, the fundamental factor that we have, it is increment BI squared, which is fundamentally the probability that we have some change in the information that we are sending. And then the second factor is the increment of VI squared minus the multiplication of increment of VI with increment of V jot. This is fundamentally the coupling capacitance between these lines. This formula set is extremely precise, even for 3D, assuming that the lines, the information that we are sending is aligned. If you assume that the information that you are sending is completely unaligned, then actually, again, you can do the same mathematical analysis and you see that you get one formula that actually is even simpler. It just depends of the square of increment of VI. In reality, the problem is that the signal get disaligned as they are transmitting, as they get propagated. If you use the classical formula to try to get the energy consumption with alignment, you are going to get MSA, which is extremely good. If you try to do the same analysis for the case of misalignment, you will see that the MSA is getting much, much worse. In this case, the simulations were something like 10 e minus 5 Joule square of degradation. If we want to improve the accuracy, even in the case of misalignment, what we can do is to add one term, here the term capacitive misaligns multiplied by 10 misaligned, that fundamentally model the effect of the variation of the energy when the patterns that propagate through our bus move over time. Just adding this additional factor decreases the accuracy, or decreases the error, increases the accuracy by something like a factor of 10. In this result, you can see in a 3D plot for all the scenarios that we were analyzing, just which is the value that we were getting for the ground capacitance, for the coupling capacitance, and then for the misaligned capacitance. The two key observations is that you see that there is one region where actually the error is slightly larger, 7 e minus 5. You have other regions that Aachen was that actually the MSB is smaller. So obviously there are some situations with misalignment is larger, where the error is slightly larger, but nevertheless with a quite, let's say, small range, quite accurate. But the other thing, which is even more interesting, is that there is a very strong correlation between the value of the misalignment capacitance and the CC and CG, so that it is almost possible to try to determine the optimal misalignment capacitance just as a function of CC and CG. This implies that probably it could be possible to produce a much more accurate model for energy consumption if we are using a principal component analysis technique. So what we did is, in addition to the traditional terms of the ground capacitance and coupling capacitance, we were adding another term, T3, that was calculated as the PCA of the result, and then 1 through 3, which is the effect of that. And you see, with that, we get one model that fundamentally had the same complexity that the standard model with the misalignment effect, but that produced one error, which is even smaller. Moreover, the advantage of this more precise, let's say, formulation is that it allows us to understand which is the energy as a function of the factors T1, T2, T3. And these are exactly the factors that we can reduce through coding. Once we have understand our technology, our next step was to try to understand the data. As an example, just because of the, let's say, the relevance today, what we did was to take the data regarding the activation and the weights that we have in different modern machine learning applications. For example, we were using a visual transformer, a swing visual transformer, and an OPT machine learning approach. We were taking the data regarding the weights, the data regarding the activation. So fundamentally, this will be the data that we saw in the previous slide, in the previous presentation, that we have to move from the memory to the hardware accelerator. We were analyzing this data. We were just calculating the typical standard deviation, the entropy that you have in the MSBs. And we were realizing that actually there was a lot of redundancy in the data. So you see that the entropy in the MSB is actually much smaller than the number 4. This means that there is a large potential for improvements in terms of low power coding. Our next step was to develop one hardware architecture that was allowing us to implement different low power codings. Maybe we can discuss that later, but fundamentally in terms of low power coding, the approaches that produces a better trade-off between complexity of the encoding approach and reduction of the transition activities are the traditional K1, K0 low power coding approaches, maybe together with the presence of a correlator. So what we did was to develop one hardware module, here you have it, that can be configured so that it can implement different low power techniques. We implemented the module in such a way that we can reduce offline the number of configuration that we have. For example, we can decide offline that we don't have the possibility of a correlation, while keeping the possibility of the inversion and the case zero. Or we want to develop another hardware that, let's say, have all the possibilities, or we just want to restrict ourselves to the possibility of sending the normal data and just to allow the configuration zero to have a case zero coding. With that, fundamentally, you can see that you can get a trade-off between the area overhead in the encoder, the energy of the encoding process, but then the total amount of the reduction in transition activity that we can get. Our last step was to analyze how much energy could we reduce in terms of the movement of data as a function of the data that we are sending. We were using fundamentally all the data that we have in the previous transformers, and what we are representing here is just which is the topology in terms of coding, which is producing the best reduction in terms of energy as a function of the coupling, ground, and misalignment effects. The first, let's say, remarkable result is that there are some combinations of scenarios in monolithic 3D where actually no coding was producing the best result. There are other scenarios where actually K0 is producing the best result. If now we move to another kind of data, you see that for this case, where actually the correlation in the data is fundamentally changing, then again, we have a couple of points in orange. This is where the point where no coding was actually working better. And then K0 with a normal correlator was actually the approach what was producing the highest reduction of low power coding. You notice if you compare the two approaches that here and here, yeah, we are getting always a different optimal low power coder. Again, we move to another scenario, we just change another kind of data, and again, we get a combination of optimal low power coding technique ranging from no coding in orange, the K0, which has a very large range of a scenario, which is the best coding. Then we have also a couple of points with K0 with the correlator, and a very small set of points with K0 and the inversions of the lines. Good. Then finally, when we take all this information into account, what we can do is just to analyze the typical data that we can that we have in our calculation. We can take the particular 3D scenario that we have, so the combination of 3D technologies, and with that, we can select the low power coding template that is producing the best result. How much energy can we use with this? So how much energy can we use if we select this optimal low power coder? Here you get the result, and you can see if we compare for the different scenarios, the case of no coding with the case of the best coding that our approach produces, we get improvement that range from a factor 3 to a factor 4.6. It means we are cutting by 3, we are cutting by 4 the power consumption that you are dissipating in the interconnect. And the price for that is just a couple of XOR gates put in a clever location. In the next slide, we are just analyzing what is the potential in energy saving that we can have when we use a standard approach like K0 versus the best coding approach that we can configure with our result. And if you see that if we do coding, we get a factor of 4 in gaining, but if in addition to that, we try to use the best coding let's say, associated with the data that we are transmitting, then we can get something like an improvement in the energy consumption of something like 2.3, something like cutting by half the energy consumption. Okay, there are other configurations depending of the particular 3D technology, where you see that actually the reduction of K0 versus the best coding is relatively small, and these are just the cases with coding with the traditional K0 that we were developing in the past is actually so good that there is no way to improve it. So summary, what we have seen right now, we have seen that it is possible with a very small amount of hardware to reduce the power consumption when we transmit data in heterogeneous monolithic 3D technologies. We can see that we can develop one configurable encoder where we can fit the coding approach to the kind of data that we have in our application. And in addition to that, we have seen that we can model the energy consumption in 3D technologies just using a extremely efficient PCA approach. With this methodology, we see that we can more or less produce a saving of a factor 4 in terms of the energy that we need for transmitting our result. I think with that, maybe I can conclude this part of the talk. So thank you very much for your attention.